let's look at some properties of Laplace transforms. Okay, first let's look at its existence, whether for a particular function does it exist or not. So existence of Laplace. Now if f of t is continuous and limit as t approaches infinity of f of t times e to the power of minus st is finite. The Laplace transform of f of t, that is, how do we write it? We write it as 0 to infinity of f of t times e to the power of minus st dt exists for s greater than a. And this, why this condition should be true for this to work out, is because if s is less than a, then what will happen? It will go to infinity. That means diverges. If s is equal to a, then it will become indeterminate, right? So that is why the condition has to be satisfied. S should be greater than a. And importantly, this is only a sufficient condition and not, or rather, but not a necessary condition, because there might be some exceptions. Okay, so that is one. By the way, in the next session, we will actually look at this with an example, right? So as of now, take it as it is. Now let's look at the second property. Okay, now the second property is that of linearity. If f of t and g of t are two functions whose Laplace transforms exists, and if a and b are any constants, then Laplace of a times f of t plus b times g of t is equal to the Laplace of the sum of the Laplace of the individual items. So this can be written as, first of all, a is there. Since a is a constant, we can take it out. Laplace of function of t, f of t, plus b times Laplace of g of t. Okay, very quickly we can see this. Remember, Laplace transform is written as integral from 0 to infinity of e to the power of minus st of, let's take this, a times f of t plus b times g of t dt. Yes. Now this we can split it up based on rules of integration. So we can say this is equal to 0 to infinity of, let's distribute this. So e to the power of minus st times a f of t dt plus integral of 0 to infinity of e to the power of minus st times b g of t dt. Now here a and b are constants, so we can take it out, right? So this becomes 0 to infinity of e to the power of minus st times f of t dt plus 0 to infinity b, we can take it out, of e to the power of minus st gt dt. And if you notice, this is nothing but the transforms, Laplace transforms of f of t plus b times Laplace of g of. Sometimes you will end up with in situations like this, that time you can just take individually the transforms. So in other words, we can write it descriptively as Laplace transform of a linear combination is the linear combination of Laplace transforms. So see here, in this case, this is a linear combination and this is the Laplace transform. So Laplace transform of linear combination is equal to what? This whole thing is a linear combination. So linear combination of the Laplace transforms. Okay, so that's what this means. Okay, now let's look at another property. This can be also written as a theorem of linearity. This can be written as theorem of existence. Okay, now the third one is first shifting property. It states if the Laplace transform of f of t is capital F of S, then the Laplace transform of EAT, I don't have to write off because I'm writing L as well. Laplace transform e to the power of at f of t is equal to f of s minus a. Let's see. Let's proceed with one side, left hand side, and see whether we reach the right hand side. So remember, we can write it as 0 to infinity of e to the power of minus st f of t we write in general, but here f of t is this entire thing. So EAT f of t dt. Now this can be written as 0 to infinity of e minus st plus at f of t dt. Again, this can be simplified by taking out common. We can say minus, we take it out, s plus, no, this will become minus now, s minus a t f of t dt. Now what we can do is, we can say, to keep things simple, we can say r is equal to s minus a. So the Laplace transform of EAT f of t is equal to capital F of r. Remember, this will become r, which can be written as f of r, which is nothing but f of s minus a. Same thing, we are writing it differently. If we don't use this r, then we would write it in this form. Okay, now that we know these properties, let's look at some elementary transforms, elementary or rather Laplace transforms of elementary functions. That we will look at it in the next session. Later on, as we go along, we will add some more theorems. Enough for now. Bye.